Welcome back, everyone. We're diving into the world of prediction today, folks. Specifically, linear and logistic regression.
That's right.
And I've got a whole stack of sources here. We've got technical explanations, comparisons, codes and cons, the whole nine yards.
Yeah, you've really done your homework.
I try. So the goal here is for everyone listening to walk away not just knowing what these methods are, but how they actually work. Like, when do you use each one? What are the gotchas? That kind of thing.
Exactly. Because these techniques, they're not just some abstract math equations,
Right.
They're the engine behind so many things we encounter every day, like recommendations you see online or credit card fraud detection.
Yeah, they're everywhere once you start noticing. Okay, so let's set the stage. You're looking at a mountain of data,
Right.
and you're trying to predict something specific.
Right.
Like, how much is this house going to sell for?
Oh,
Or what's the temperature going to be next week?
okay.
That sort of thing. Where do you even begin?
Well, if you're predicting a continuous value, like those examples you just gave, temperature, sales figures, things like that, your go-to tool is linear regression.
Linear regression. All right, break that down for us.
Sure. Imagine you've got all your data points scattered on a graph. Linear regression is essentially finding the best fit line through all that chaos, the line that's closest to all those points.
Okay, so it's like finding the average trend, the line that kind of represents the overall relationship between all those data points.
You got it.
And the cool thing, right, is that line can be represented by a simple equation, right?
Absolutely. A linear equation, just like you learned back in algebra class. Y equals mx plus b, that sort of thing.
Right, right. And that equation is super useful because then you can actually use it to make predictions.
Exactly. Plug in a value for x and out pops your prediction for y. But behind the scenes, there's a little bit more math happening. We use something called a cost function to figure out how well our line actually fits the data.
Okay, a cost function. So is that like measuring how far off our line is from each data point?
Pretty much. It's like we're calculating the total distance between our line and all those points, and we want that distance to be as small as possible. The smaller the distance, the better our line fits the data.
Makes sense. So we want to minimize that cost. But how do we actually go about finding the best fitting line, the one that minimizes that cost function?
That's where gradient descent comes in. Imagine you're trying to get down a mountain, but it's super foggy, you can't see anything.
Oh, I don't like that. I'm not a fan of heights.
Well, gradient descent is like you're feeling your way down, taking small steps in the direction of the steepest descent.
Okay, I can picture that.
Eventually, you'll reach the bottom of the valley where the error, or cost function, is as low as it can go.
So we're using this algorithm, gradient descent, to find the line that best fits our data by minimizing that cost. Pretty clever.
Yeah, it's a really powerful technique.
But what if our data is a bit more, I don't know, complex? And a straight line just doesn't really capture what's going on.
That's a great point, and that's where we can run into the problem of overfitting.
Overfitting. I've heard that term thrown around.
Yeah.
What does that mean exactly?
Well, it's like when you study for a test by just memorizing the answers without actually understanding the material. You might ace that specific test, but you're not really learning anything, are you?
Right.
Overfitting is kind of like that. The model learns the training data too well. It becomes really good at predicting the data it's already seen, but then it fails miserably when it encounters new data.
So it's like our model is a one-trick pony. Great at one specific thing, but not very adaptable. How do we make sure our model is more of a learner, not just a memorizer?
Well, there's a technique called regularization that can help with that. It's like we're adding a penalty for complexity. We're basically encouraging the model to find a simpler line, even if it doesn't perfectly fit every single data point in our training data.
So it's like we're saying, hey, model, don't get too caught up in the details. Look for the bigger picture.
Exactly. And that helps the model generalize better to new information.
Interesting. So we're preventing it from becoming too specialized, too overfit to the training data. Now, I know that linear regression has a ton of applications in the real world. What are some examples from those sources you were looking at?
Oh, it's used everywhere. In finance, people use it to predict stock prices or assess risk. In healthcare, you can use it to analyze patient data and maybe estimate the likelihood of certain medical conditions. And in marketing, linear regression can help you understand how different factors influence sales.
Wow. So it really is a versatile tool, from predicting the stock market to figuring out what makes people buy stuff.
It's a foundational technique, and it can be incredibly powerful when used correctly.
Okay, so we've got a pretty good handle on linear regression, but what about when we're not trying to predict a number, but more of a category?
Okay.
Like, will a customer click on this ad? Or is this email spam or not?
Right. So instead of a continuous outcome, you're looking at a binary outcome.
Yeah.
Yes or no, true or false, that sort of thing.
Exactly. Is linear regression still the right tool for that kind of prediction?
Not quite. When you're dealing with categories, logistic regression is your friend.
Logistic regression.
Mhm.
All right, let's dive into that. What's the key difference here?
Well, with logistic regression, instead of predicting a specific number, we're predicting a probability, a number between 0 and 1.
So if I'm trying to predict if someone will click on an ad, logistic regression wouldn't tell me they will or won't, but it would give me a probability score.
Precisely, like an 80% chance they'll click or a 20% chance they won't.
Okay, so it's more about the likelihood of something happening, not the exact value.
Exactly. And just like in linear regression, that probability is based on a weighted sum of the input features.
Okay, so we're still using those weighted features.
Yep, each feature gets a weight representing its importance, just like we talked about with linear regression. But there's a little twist here.
A twist. I like twists.
To make sure our output is a probability between 0 and 1, we use something called the sigmoid function.
Sigmoid function. Sounds intimidating.
It's not as scary as it sounds. Think of it like a volume knob. It takes whatever number comes out of that weighted sum, no matter how big or small, positive or negative, and squishes it down into that 0 to 1 range.
Ah, I get it. So no matter what the weighted sum spits out, the sigmoid function makes sure we get a nice, neat probability as our output.
That's exactly right.
Pretty neat. And I'm guessing interpretability is still important, right? We still want to know which features are driving those predictions.
Absolutely. Just like with linear regression, we can look at the coefficients in our logistic regression model to see which features are pushing the probability higher or lower.
So we can still see which features are the most influential, the ones that matter most.
You got it. For example, let's say we're trying to predict customer churn. Will a customer stick with our service or will they leave? Logistic regression can help us identify which factors are most likely to make someone churn. Like maybe they haven't been using our product very much lately, or they've had some negative interactions with customer support.
Oh, I see. So not only can we predict if someone's likely to churn, but we can also get clues about why.
Exactly. And that's incredibly valuable for businesses because then they can try to address those issues and hopefully prevent customers from leaving.
Makes sense. It's not just about predicting the outcome, but understanding the factors driving that outcome.
Right. You want to be able to act on that information.
Okay, so we've got these probabilities now, but how do we actually make a decision? It's not a simple yes or no anymore.
That's a good question. So what we do is we set a threshold, let's say 0.5. If the predicted probability is above 0.5, we predict yes. If it's below 0.5, we predict no.
So it's like drawing a line in the sand. Above the line, it's a yes. Below the line, it's a no.
You got it.
But choosing where to draw that line, that threshold, seems kind of arbitrary.
Yeah.
Are there best practices for finding that sweet spot?
It really depends on the situation and what the consequences are for making different kinds of errors. Like, if you're predicting if a transaction is fraudulent, you might want to be extra cautious and set a higher threshold. Even if it means you sometimes flag legitimate transactions as fraudulent, you really want to catch those fraudulent ones.
Ah, so there's a trade-off. We have to weigh the costs of different types of errors.
Exactly.
Now, I'm guessing we also have specific ways to measure how well our logistic regression model is performing, right?
Yeah.
It's not just about accuracy anymore.
You're right. Accuracy, which is how often the model gets it right, is still important. But we also look at things like precision and recall.
Okay, precision and recall, those sound familiar. Remind me what those are again.
Sure. Precision tells us out of all the times the model predicted yes, how many of those were actually correct.
Oh, okay. So it's like, how trustworthy are the yes predictions?
Exactly. And then recall measures out of all the actual yes cases, how many did our model correctly identify?
So it's about making sure we're not missing any of those important yes cases.
Exactly. And depending on the problem we're trying to solve, one of these metrics might be more important than the other.
Got it. So we have to choose the right metric to evaluate our model based on the specific problem we're trying to solve.
Exactly. There's no one-size-fits-all approach.
This has been super insightful. So we've explored linear regression for predicting continuous values and logistic regression for those categorical predictions. And it's really cool to see how these methods, which seem kind of straightforward on the surface, can be applied to such a diverse range of problems.
Yeah, it's pretty amazing.
But I'm sensing a theme here. Both methods seem to rely on these linear combinations of features.
You're picking up on something important there.
What exactly does that mean, and how does it play out differently in each model?
You're asking the right questions. Let's dig into that a bit further. You're absolutely right. That idea of linear combinations is at the heart of both linear and logistic regression. It's like each feature gets a vote in the final prediction, but some votes carry more weight than others.
Okay, so each feature has a certain weight that represents its importance in the prediction. And the model combines these weighted features to come up with the final prediction. But how does that actually work? Can you give me an example?
Sure. Let's say you're baking a cake, right?
Okay, I'm following.
You've got different ingredients: flour, sugar, eggs. Each one contributes something different to the final product. In our models, those ingredients are the features. The weights are like the amounts you use of each ingredient. A higher weight means that feature has a bigger impact on the prediction. Just like if you use more sugar, your cake's going to be sweeter.
I love that. So the model is like a recipe, mixing together these weighted features to bake up a prediction. But I'm a little confused. I thought logistic regression output a probability, while linear regression predicted an actual number. How did that work if they both use this weighted sum approach?
That's a great observation. They both start with that weighted sum, but that's where they diverge. Linear regression just uses that sum directly as its prediction. It's
Yeah.
like saying, based on these ingredients, this cake is going to bake at 350 degrees for 30 minutes. Straightforward.
Okay, I see.
Logistic regression, on the other hand, takes that weighted sum and runs it through the sigmoid function. Remember our volume knob? It takes that sum and transforms it into a probability between 0 and 1. It's like saying, based on these ingredients, there's a 70% chance this cake is going to be delicious.
Ah, now that makes sense. So they share the same foundation, but they use different techniques to get to their respective outputs. But every model has its limitations, right?
Yeah.
What are some of the things we need to be careful about when using these methods? What could trip us up?
You're hitting on a key point. One of the big assumptions with these models, both linear and logistic regression, is linearity.
Linearity, right?
Then they assume there's a straight line relationship between the features and what we're trying to predict. But the real world is messy. Relationships are rarely that simple.
Yeah, life's not always a straight line.
Exactly. Trying to fit a linear model to data that's curvy or has jumps is like trying to draw a straight line through a winding road. It's just not going to capture the true path.
So we need to be mindful of that assumption and make sure it actually makes sense for the data we're working with. What other red flags should we be on the lookout for?
Well, outliers can be a real headache. You know those data points that are way off from all the others?
Oh yeah, the oddballs.
Those outliers can have a huge influence on our models, and not in a good way. It's like having one super strong ingredient in your cake batter that overpowers everything else. It throws off the entire flavor.
Oh, I've been there. One time I accidentally put way too much salt in a recipe. It was not good.
Yeah, not a good time. So with outliers, sometimes you might need to remove them, especially if you think they're due to some kind of error in data collection. Other times, you might try transforming the data to lessen their impact.
So it's like adjusting the recipe to balance out that overpowering ingredient.
Exactly. You have to use your judgment and figure out the best approach for the situation.
Makes sense. Data preparation sounds like a whole art form in itself. What other challenges might we run into with these regression methods?
Well, multicollinearity is another one to keep in mind, especially when you have a lot of features. It's basically when two or more features are highly correlated, they're telling us the same story.
So it's like having two witnesses to a crime who give almost identical accounts. It's hard to know what's truly important and what's just an echo.
That's a great analogy. And when features are highly correlated, it can mess with the model's ability to figure out the individual impact of each feature. The weights can become unstable and hard to interpret.
It's like having two ingredients in our cake recipe that taste almost the same. You can't tell which one is contributing more to the overall flavor.
Exactly, and there are a couple of things we can do to address that. We can do feature selection, which is basically choosing the most important features and getting rid of the redundant ones. It's like picking the key ingredients for our recipe and leaving out the ones that won't make a big difference.
So we're simplifying the recipe, making it more focused.
Right. Or we can use dimensionality reduction techniques, which create new features that combine the information from those highly correlated features in a more compact way.
So it's like we're making a more concentrated version of our recipe, extracting the essential flavors without the redundancy.
Exactly.
This deep dive is really highlighting that using these models is not just plug and play. There's a lot of thought and careful consideration involved in choosing the right approach and addressing these potential pitfalls.
Absolutely. Data analysis is an iterative process. You need to understand your data, try different models, address those potential issues, and evaluate the results carefully.
It's a journey, not a destination.
It really is. And sometimes the most interesting insights come from those unexpected detours along the way.
Speaking of detours, I remember our sources mentioned that both linear and logistic regression have been extended and improved upon over the years. There's been a lot of innovation built on top of these fundamental methods, right?
Absolutely. Data scientists are always looking for ways to refine these techniques and make them even more powerful.
That's right. It's not like they've just discovered these methods and said, okay, we're done.
Right. So what are some ways they've, I don't know, souped up these classic techniques?
Well, one cool extension of linear regression is something called polynomial regression. It's like giving linear regression a power-up to handle those curves and bends in the data we were talking about earlier.
Okay, so instead of just assuming everything's a straight line, we can now handle those more complex relationships.
Exactly. Instead of just using the original features, we add in these polynomial terms like squaring or cubing the features.
Right.
It lets us capture those more intricate patterns. So it's still based on linear regression, but it's a bit more flexible, more adaptable.
Precisely. It's like adding extra ingredients to our cake batter to create a more complex, nuanced flavor.
I like where this analogy is going. What about on the logistic regression side? Have there been any interesting developments there?
Oh, absolutely. One really cool extension is multinomial logistic regression.
Multinomial.
Yeah, so it lets us handle situations where we have more than two categories. Like imagine you're trying to predict not just if someone will click on an ad, but what type of product they're most likely to buy. Apples, oranges, bananas, you name it.
Oh, I see. So instead of just the yes-no probability,
Yeah.
we get a probability for each possible outcome.
Exactly. And the model can tell us which outcome is the most likely. It's like the model has become a taste tester, predicting which fruit the customer is most likely to enjoy.
So we've gone from predicting a single number to predicting a whole set of probabilities.
That's right. And that opens up a whole world of possibilities for what we can predict.
It's amazing to think that these methods, which seem pretty simple at first glance, have evolved into this whole family of specialized tools.
It's a testament to the ingenuity of data scientists. They're always pushing the boundaries, finding new ways to tackle ever more complex problems.
And that's just the tip of the iceberg, right? There's a whole universe of machine learning algorithms out there building on these fundamental
Well,
ideas.
absolutely. You've got decision trees, support vector machines, neural networks, the list goes on. And each one has its own strengths and weaknesses, best suited for different types of problems.
It sounds like a lifetime of exploration just waiting to happen. Well, folks, I think we've covered a lot of ground today in our deep dive into linear and logistic regression. You've learned the core differences between these two powerful methods, when to use each one, and some of the key concepts that make them tick, like linear combinations of features, cost functions, gradient descent.
And importantly, you've gained an appreciation for the assumptions these models make and those potential pitfalls that can trip you up along the way. Things like nonlinearity, outliers, multicollinearity.
Armed with this knowledge, you can approach these methods with more confidence and start applying them to your own data.
But remember, folks, this is just the beginning. The world of data science is constantly evolving. Keep exploring, keep experimenting.
And keep those questions coming. We'll leave you with one final food for thought. Imagine you've got a data set with both continuous and categorical variables, a real mixed bag, and you need to predict something pretty complex, something that depends on all those different types of variables. What kind of model would you choose? How would you approach that challenge? Something to ponder as you continue your data science journey. Until next time, happy predicting.